Hi, grade 12s. Happy Monday. I've been getting a lot of questions about page 428. Let me page 428, number 5 and 7. Let me just make sure. I think that's everybody was asking about those questions, and they are about neutralizing and titration. Okay, so number 5, after titrating sodium hydroxide with hydrofluoric acid. Okay, so sodium hydroxide plus hydrofluoric acid. This is going to form sodium fluoride plus water, so neutralization. Let's label them. This is strong base, and this is a weak acid. Okay? And so that means when you look at the conjugate base, there's going to be sodium and, sorry, not conjugate, neutralized salt. There's going to be sodium, which is acting as a very weak acid, and then there's fluoride, which the fluoride ion. Do you see how whatever is weak is going to be strong on this side? Okay, so I have a strong conjugate base with fluoride that now in a neutralized solution is going to react with water to go back to being hydrogen fluoride molecule plus hydroxide. So a weak acid will produce a slightly basic solution. A weak base is going to produce a slightly acidic solution, because it's always a weak acid or base is going to form a strong conjugate acid or conjugate base. So we have that out of the way. And it's saying a chemist determined that the reaction had formed an aqueous solution of 0.020 moles per liter of sodium fluoride. Determine the pH of the solution. So it's already telling us that the concentration of this over here is 0.20 moles per liter. So guess what? I'm going to go make this ice table, and they already gave me my concentration. Again, I don't worry about water. And because it was completely neutralized in this reaction, you have 0 for initial concentration, 0 for hydrogen fluoride, and 0 for hydroxide. Okay, here it's obviously going to shift to the right. Okay. And so this is our equilibrium table. What I need to find, though, however, is I need to find the Ka of hydrofluoric acid. So let's see. Oh, those are bases. I'm in 8.2 right now. I'll tell you which page. Okay, on page 369. I find that the Ka for hydrofluoric acid is equal to 6.6 times 10 to the minus 4. Thank you. Since what is acting, I'm going to use this highlighter, this is not hydrogen fluoride. So this number is not useful to me. What I have to do is I have to find the Kb, which is going to be Kw divided by Ka. So 1.0 times 10 to the minus 14 divided by 6.6 times 10 to the minus 4. And I get 1.0 times 10 to the minus 14 divided by 6.6 times 10 to the minus 4 is 1.52. All right, let's do 1515, it's repeating, times 10 to the minus 11. So that's my KB value. What am I using my KB value for? For the equilibrium expression of this up here. So KB is equal to X times X over 0.020 minus X. And if we do the 500 rule, it is, if we do 0.020 divided by KB, it's going to be negligible. So let's just get rid of that. So I'm going to set it up to 1.51. Keep it going, times 10 to the minus 11 equals X squared divided by 0.020. Okay, so to our calculator, we're multiplying the number by 0.02, and then we're square rooting it, and I get an X value of 5.50 times 10 to the minus 7 mole per liter, which this is important because this is my concentration of hydroxide. Let's go back to the page. Where am I? 428. Okay, and we should have two numbers as significant, whatever. I'll get rid of this 0. So what I'm going to start off with is finding the POH, so negative log of the answer, and I get 6.259, and so the pH is 14 minus the POH. 14 minus the answer is 7.74, or 7.7 following significant digits. Okay, and let me just, it'd be awful if I showed this to you. I got the wrong number, I got it wrong. So this is chapter 9. Yeah, number 5, 7.74. And then, so that's how you do that question. Now let's look at number 7. We have benzoic acid is titrated with sodium hydroxide at the same concentration, calculate the pH of the of equivalence. So we have benzoic acid, which is a weak C. Okay, so this is what's going to be, really this is going to be 100% this way, because we have a strong base reacting with a weak acid. So think about it. Weak acid is going to produce a solution that is weakly basic. So we're going to have something above pH of 7. So the conjugate is going to be C6H5COO minus with Na plus. So because this strong produces weak, I don't care about this, but weak produces strong, this is the species that I'm going to react with water. So I have C6H5COO minus aqueous plus water. So this is going to be an equilibrium. And this is going to produce hydroxide ions. So it's going to go back. Do you see how this is the same as this? It's just reacting with water and going backwards and going back to the weak acid. But the reason why weak acids produce a weakly basic solution is because of the hydroxide ions that are being produced. To explain that a little bit further, this species here is not dissociated, so that hydrogen is not available to participate in in chemical reactions. Okay, so they're stuck together now. There isn't that hydrogen that's able to move around. And whereas these hydroxides, they're going to act like bases. Okay, and I said, what page was it on? 369. We have to go look at, oh, I gave the wrong page. I'm terrible for giving you guys wrong pages. Or was it 396? It was 396, typical move. Sorry guys, 396 is where you find your Ka numbers. So the Ka is going to be for, this is benzoic acid. Is it? It's not there. So did it give us? I guess you have to look in the back of the book, or let's just look on here. So the Ka of benzoic acid. Okay, so the Ka, thank you Google, is 6.5 times 10 to the minus 5. Again, we have to work with the Kb, which is Kw divided by Ka. 6.5 divided by, oops, that's the Ka. Have to do the other way. 1.0 times 10 to the minus 14 divided by 6.5 times 10 to the minus 5. And I get 1.538 times 10 to the minus 10. Oh, and then we forgot to do our ice table. So I'm just going to do my ice table down here. And then I'm starting off with, okay, and here's the other thing. It's a 1-to-1 solution. So 0.025 moles per liter of benzoic acid is titrated with 0.025 moles per liter of sodium hydroxide. Because they're going to be added in equal proportion, so 0.25, because they have the same molarity, when you add them together, it's going to be the same volume from each of them, volume 1 plus volume 2, which means in here it's going to be twice the amount of volume, but the same concentration, or sorry, not the same concentration, the same amount of molarity. So what happens is that the concentration halves. Okay, so again, if this is the acid, and it's a 1-to-1 neutralization, acid with the base, so you know down here that this, what would it be, sodium benzoate, that is going to be, there's going to be 0.25 mole per liter, but in twice the amount of volume. So because there's twice the amount of the volume, one volume from the acid, one volume from the base, you divide it by 2. So I'm dealing with 0.125. Oh, Nolan's talking to me. And this all looks very familiar, right? And ta-da. Now we can start dealing with the Kb value. 1.5385 times 10 to the minus 10 equals x squared over 0.25 minus x. I can, I can approximate this. 0.25 divided by 1.5385 times 10 to the minus 10 is going to be way over 500. So I'm just going to get rid of this. And I'm going to find the square root The answer is 6.20 times 10 to the minus 6 mole per liter, which again is going to be my concentration of hydroxide. So the first thing I'm going to do is find the POH, which is the negative log of 6.20 times 10 to the minus 6, negative log of the answer, and I get 5.207, and pH is 14 minus 5.207, and I get 8.7925. Okay, and I think that's about what got in the answers, and the answers are found on page 455. Let me see. 8.15. It's a little bit off. Maybe it's because of this over here. That's close enough though. Okay, all right, so let me know if I can help you further. And the test will still be on Wednesday. I'm just going to give you guys longer time to work because of the conflicts with calculus.